YouTube. I'm back from a week ago. Let's see, a week ago I posted a video about printing a hexadecimal character, say something stored in memory, to the screen, and we finished by printing the magic number, I believe, to the screen by accessing it. So now what we're doing is we're going to go from that and to talking about the A20 line. Alright, so first we need to discuss what the A20 line is. So in older microprocessor architectures, like Intel's 8086 and 8088, the processor had 20 bits in an address bus ranking from A0 as the least significant bit to A19 as the most significant bit. This allowed the processor to access 1 megabyte of memory, but as you may have picked up on, there arises a problem, and that is that the 8086 was a 16-bit processor, and so therefore they couldn't directly access the 20-bit address that was given to them in memory. And that meant that they had to come up with a clever way around it, which was segmenting. And we've talked about segmenting a little bit, but here we're going to explore it more and really understand what it is. So to do this, the 8086 used an offset address, and they used a segment address. And the offset, let me just go ahead and get in here, just kind of started a template here with a label. Anyway, the offset address ranged from 0x0000 to 0x FFFF. That's the offset. Whoops. And the segment ranged from 0x0000 to 0xF000. And that made it possible to access that extra, or those extra, 4 bits. Well, 4 bits for the memory bus. And the way the final addresses of these segments was calculated is as follows. So the notation was segment offset, alright, and the final address was calculated as equal to the segment times 16 plus the offset. So if you had, let's say, make this easy to see, a segment, or if you had the segmented address, 0xF000 and 0xFFFD or something like that, then the final address would be 0xF000 times 16, which, since we're in hex, that it's basically like multiplying by 10 in decimal, so you just add a 0. Whoopsies, plus 0xFFFD. And that equals 0xFF, so that and then plus the offset FFFD, right? So that's an easy example. Obviously, they can get a little bit more complicated in that sometimes you actually have to add hex with characters with hex characters instead of just a 0, but that's the underlying principle. And that is a 19-bit number, or it's actually a 20-bit number, but regardless, it's that allows you to get up to that 1 megabyte. But there were certain scenarios that could also be implemented. As you might have noticed, F000, which is the largest the segment register was supposed to be, could obviously be bigger. I mean, it was a 16-bit register, so you could conceivably go up to FFFF, right? So if you look at the address F800, say that's your segment, and your actual address or your offset is 8000. Well, when you segment that equals 8000 plus 8000, which equals 100,000. And that is now a 20-bit number. Or, well, it's a 21-bit number. It goes, so it requires the 20th address bit, with the least significant bit being the 0th address bit, right? So all of a sudden, you don't have enough width in your address bus to take in this piece of data and preserve it. So what it ended up doing when it tried to copy that into the address bus was just truncated the 1. And all of a sudden, look where we are. We are at address 0. We have wrapped all the way back around to the starting address. And developers of the 8086, for some god knows what reason, thought it was a really good idea to utilize this feature of the 8086 architecture to basically just perpetually add onto your memory bus or your memory addresses and go back, basically just add and go anywhere in memory because of that wrapping. So unfortunately, since we like to have backwards compatibility with those older era programs, there is an option that you can that sometimes upon booting BIOS will have automatically enabled or disabled. That is the A20 line. So if the A20 line is enabled, then that 100,000 will be written to your address bus using, and it will be completely preserved. That 1 will not be truncated because there will be the proper number of bits to represent that data. But if the A20 line is disabled, then it will truncate and you'll go back to the start. You'll wrap around. So since we are not trying to write software or an operating system that is compatible with 8086 programs, we're trying to write a 64-bit operating system, we don't want the A20 line disabled. We want it to be enabled. And at this point, you should be able to conceive an easy way to figure out if it's properly enabled. And that is by looking at a location in memory where the information in that spot is always constant, and comparing that location in memory with the segmented location. And if the segmented location is equal to it, then you know that it's wrapped and the A20 line is disabled. And if it's not equal to it, something different, in our case it'll probably be a bunch of zeros, then you know that the A20 line is enabled and it's at some completely different location in memory, likely exactly where it should be. So let's go ahead and now that we understand that, let's go ahead and figure out what we're going to use as our reference. And an easy thing that just first pops to mind that we as a word we can use to our reference would be our magic number. All right, that's always going to be at the same location, and it's always going to be AA55, right? So that, as it turns out, if we go into our main, BIOS has loaded us through our specifications into 0x7C00. Alright, so that's where kind of we start. Then our magic number is right here. So the word AA55, and it's located 510 bytes from 7C00. And we already did this last time. Actually, let me get rid of this. I was doing a little bit of testing earlier. Alright. We already know that. We've already printed it. So we print it, AA55, right, that's where we left off last time. So let's go ahead and let's set up something similar in our test A20 with segmenting. So now we need to figure out how we're going to segment these so that we know we are accessing 1 megabyte ahead of where we are currently. So that way we can wrap or not wrap. So this first segment we're going to set up was going to be for our starting address, which is, remember, 7C00 plus 510. And it turns out that that actually is equal, if you do the math and you add it, it's 7E0E. Or, no, it's not. That's 7DFE, sorry. So let's go ahead and let's set up our segment register first, and then we can set up our offset register. So if you recall way back in, I don't remember what video I talked about this. Maybe it was the first video. I don't remember. Maybe I haven't. Regardless, segment registers cannot be assigned a value directly. So you can't just say move ES2 or something like that for your ES segment register. It doesn't work that way. It's going to throw an error. But what you can do is you can assign them indirectly. So to do this, let's just go ahead and let's just push all here real quick. And then let's push BX. Let's move to BX. Well, let's just make it 0, so XOR BX. And move into ES BX, so that way our segment register is set to 0. And pop BX. Alright, so the deed's done. Now let's move into BX 0x7DFE, which is where our magic number should be located. So if we move into DX, which recall is the register that our printH function reads from, if we move into their location, ES BX, and then call printH, let's go ahead and pop A and return down here, then we should be getting a 0xAA55. Let's make run. Oh, good lord. Yeah, it'd be really helpful if I actually called the function. Alright, so I've already included it. Let's go ahead and call it. Okay. Call test A20. Alright. There we go. 2 AA55s. Alright. Now, just so we don't confuse ourselves, I'm going to go ahead and just get rid of this one here, so that way we're just reading from our test A20 function. Alright, and then let's just go ahead and set up a comparison here. So move into AX 0x7E0, or I'm sorry, 7DFE. Getting ahead of myself. Alright. And then move into DXAX, call printH. There you go. Alright. So now we should also print 2. We're not going to test it, but okay. So now that we've got that figured out, we can figure out what the segment is going to be for our 1 megabyte advance. So we know that this is going to require a little bit of algebra. Nothing too fancy though, so don't be discouraged. We know that our formula for segmentation is our segment times 16 plus our offset, right? So we know what our segment's going to be. Let's just keep it simple, like we did earlier. So instead of 0, 0, 0, 0, let's just make it 0x FFFF, right? Because we can't have it be 0, so let's just have it be the next best thing. And we know that, so since that times 16 is FFF0. We don't know what our offset is, so we'll just type in offset, and we know what we're supposed to come up with. So 1 megabyte is 0x100,000, so 0x100,000. That's probably not the right way to say it, but it's the easy way to remember it. 100,000. Alright, we know that our current location is 7DFE, so basically it's 100,000 plus 7DFE. So we can just go ahead and type in 7DFE, right? And that's where we're supposed to end up. So now we just have to do a little bit of algebra, subtract over the FFF0, so it's offset equals 0x10 minus 0xFFFF0. And from there, we know that our offset equals 0x7E0E. You can do the algebra or the subtraction if you want. I'm not going to show it because I'm lazy and I know already have it figured out. But that's what it is. I kept getting ahead of myself. But yeah, so that's what our offset needs to be now. So let's go ahead and let's comment this all out. Let's go ahead and change our offset to be 7E0E. And let's change our segment to be FFFF. So we can actually do I'm confused. Well, conflicted on which is cheaper. You could do it two ways. You could say move bx 0x FFFF, right? That's one way you could do it. You could also do it by keeping the XOR bx, and then you just say not bx. Both are equally valid. I think that I'll just go with move. It takes up one line instead of two. Alright. So then, if the A20 line is enabled, we should just get some garbage data. And if it's disabled, we should get AA55, right? Let's test it out. Oh, it's garbage data. So, this means one of two things. This means, well, this means that either we access the wrong point in memory, and the A20 line might be enabled, or it might be disabled, or it means that we did everything right and the A20 line is in fact enabled. So let's go ahead. There's an easy way we can disable the A20 line on purpose. Main.asm. I've commented it out over here. Let's see. Oh, I haven't. Well, I did at one point in time. Yeah, let me go ahead and just write this out. I'm going to have to look this up. I don't remember it off the top of my head. I thought I had it commented, but that's other stuff. So, yeah, be back in a jiffy. Okay. So the problem was, alright, so I didn't, for some reason, didn't keep this. Not sure exactly why. But to disable it, all you have to do is move AX to 0x2400 and then call interrupt 0x15. Alright. So now let's make this make run. Ah, look at that. So we are indeed accessing the right spot. So that's a good sign. So now we can tell if the A20 line is enabled or disabled. However, according to oneosdev.org, proper procedure for doing this isn't just checking once. The proper procedure for doing this is then also moving your address over 1 byte and checking that as well. So in case you come across some freak occurrence, you're not fooled. So what we've done is we've just checked it 1 time. Now we need to check it another time. So let's go, get rid of Kimu. There we go. So we're over here. So now we've got AX. Remember, that's our one to compare. So yeah, let's compare AX and DX. If they're equal, so JE, then we will continue. So let's go to our continue label, which we will now create. If they're not equal, we just continue here. So then we can jump to exit, which we'll put down here. So for exit, we'll move AX to 1, just give us something to look at so that we can tell if everything worked correctly. And well, actually, no, if that's, yeah, we could use a label, but let's just pop everything right now up here, move AX 1, and return. Okay. Alright, so if everything was equal, now we're down here to continue. So we shift everything over 1. So now we can set our reference to 0x7 DFF. And we can move that and call print H. Alright, before we get too far gone, let's just go ahead. Whoops, do we have a... Oh, right. Okay. That looks good. And now let's go ahead and segment. So we can move to, well, first let's push BX, move to BX, 0xFFFF, move to ES BX, pop BX. And then move to BX 0x7E E0F. Move to DX, our segment. Call print H. Okay. And they are equal. So this is now a confirmation that tells us, yeah, it's actually disabled. So we could, I guess, keep doing this, but OSDev says that best practice is to do it twice, and if it happens twice, you can make a pretty darn good bet that the A20 line is disabled. So we've done it twice, and whatever OSDev says is good enough for me. So now that we've proven that, we just need to compare it again. So compare AX to DX, and if they're equal, then we go to exit, and if they're not equal, then we do this. So pop A, XOR AX, AX. So set AX to 0 if they're not equal. Wait a minute, hang on. So 1 should be our error. So this is if they're not equal, it's 1. If they're equal, if they're not equal. Okay, so yeah, no, we want to set AX to 1. And if they are equal, we go to exit, so dot exit. This is where we call our XOR. And return. Okay, there we go. So now we say that we do our test here, we set up a reference, we set up our segment, we compare a segment with our reference. If they're equal, we move down here and we keep going. If they're not equal, we pop everything, set AX to 1, signal that they're not equal, and we return. Down here, we move, if they are equal, as I said, we offset now by 1 byte. So we move everything over by 1 byte, do the same thing with our segmenting and comparing. If they're equal, we go to exit where we set AX to 0. And if they're not equal, we don't go to exit, we pop everything, set X to 1, and return. So now what we should be able to do is come down here. We call our test A20, right? Now we should be able to move move to DX AX. Print H to confirm that AX is indeed 1 or is indeed 0. Oh, come on, what have I missed? Oh, this isn't our main. Line 40. Oh, I forgot a comma. Whoops. Alright. Okay, so we can indeed see that A is 0. Now if we go into our main.asm and we comment out this code that purposefully disables the A20, we can see that A is set to 1 because they are not equal. Alright. And that is how you test the A20 line. So, in the future, next video, we're going to talk about the 3 ways that we go about enabling the A20 line if it is indeed disabled. In our case, since QEMU loads us up with it already enabled, then technically we don't need to worry about it, but we want to consider all operating systems or all BIOSes that might put us in all sorts of different locations or settings or whatever. So we're going to talk about ways to enable it. And then after that, we're going to start talking about our global descriptor table, which is important for using memory outside of just 16-bit real mode. So we're getting real close to being finished with our bootloader. I hope you continue to watch this series. It's kind of a fun exercise making. Also, in case you couldn't tell, I have, well, if you can't, it's not a big deal. Anyway, I have put some of this stuff on GitHub, and by some of it I mean all of it. So the reason why I say, in case you couldn't tell, is because I navigated to a Git directory. But if you, in the description there should be a link to my GitHub page where you can look at the code that I have. It's also worth noting that on GitHub is where I have my printf or printH function with the loop. So if you wanted to look at that to compare what you've done, or just because you're lazy and you want to look at the way I did it and copy it, that's perfectly fine too. It's all on GitHub, so I'll put a link to that in the description. I've also got links to other resources and stuff in the description. I'm right now working on writing up a kind of a report thesis type thing on this whole experiment. So I don't know when I'll end up publishing that or how I'll publish it, probably WordPress or something because I'm cheap. So be looking forward to that in the future when this project is completed. Yeah, that's about all I can think of. A lot of stuff is going down right now, so hope you tune into the next video, and I'll see you then.